Hello, everyone. Dr. Shane back with you here. And if you're just curious about when I'm recording this and what's happening in the world, I believe this is Monday, June 29th, 2026. And we are at the beginning of a fairly large heat wave here in central Pennsylvania. Just to kind of situate it, if you're listening to this, you can think about where you were at the end of June 2026. So, as I noted on the D2L shell, I'm trying something a little bit different here, and rather than just typing, a page worth of text in the D2L window for chapter 10 or part 3 that we're transitioning to, I'm just going to do like a little intro video here, try not to ramble too much, and just to get us caught up to where we are content-wise in the course. We've now finished part 1 of the course, chapters 1 through 4 on atmospheric chemistry and part 2 on climate change, which also has a section on nuclear chemistry in chapter 9. We're largely going to leave, what would that be then? Chapters 5, 6, 7, and 8. Those are on climate change. And in my experience, students come into this course if they know a fair amount about some aspect of environmental chemistry, it is climate change. And when it comes to the science of climate change, which comes down to primarily something called the greenhouse effect, historically known as the hothouse effect. I actually kind of prefer that term to greenhouse effect. The chemistry is fairly straightforward, so we might not do a lot with it as a class, but I'm going to have you do pieces of that as an independent project. Really what it comes down to, the science behind it, and it can go as far as you want, but it's covalent bonds are like springs and they go back and forth with a certain frequency. And if those bond frequencies happen to correlate with the infrared region of the spectrum, the heat trapping region of the spectrum, that's not a great way to describe it, but that's kind of the way it is. If it resonates with that, those chemicals tend to absorb heat more and trap heat more. So the molecule we always talk about is carbon dioxide and the two double covalent bonds, but there are plenty of other greenhouse gases that go up into the atmosphere. Methane is a very potent greenhouse gas, the primary component of natural gas. But we'll leave that largely up to you for your semester project and as part of the final exam. So that's probably been explained previously there, but just to get you, why are we jumping ahead so far um, in this course and skipping a lot of stuff? Also, as I noted, I'm just going to note it here as well, is chapter 9 on nuclear chemistry. I think is a pretty important chapter for contemporary society. They're all important chapters, but the question is, where are we spending our time together in this course? And I do want to spend some time on nuclear energy, and that's an area that I'm pretty familiar with, not just for preparing for this course, but throughout my professional career. So I'll share some things with you there. So, but without delay, what I'd like to do here, and we're already about 3 minutes into this, is just to give you an overview of part 3. So this is chapters 10, 11, and 12. And I think I called this, I'm going to do a flip through. I think that's what you call it. Like you're just going to flip through the book or flip through something and talk about it. And I'm not going to go through page by page and do that, but just to give you an overview of where we're headed. Okay, and also do a little bit of show and tell to generate some more interest. There's no shortage of examples about water chemistry and water pollution. Water is one of the most important topics we can talk about in science or just culturally. You don't have to go very far. You could probably look at a news website, or if you still read a newspaper like I do, you'll find something about water everywhere. Okay, so there's no shortage of specific case studies. One in particular that you might like to look at is, I put this link here. Hopefully the link works when you look at the slides. But there was a great documentary on PBS called Poisoned Ground. And it was centered around a place called Love Canal, which is near Niagara Falls in the state of New York in the United States. And this is a pretty tragic story where chemical companies were effectively just dumping waste into rivers and then into the soils with giant 55-gallon drums without any kind of regulation. Back in the, I believe it was like 60s and 70s, you can kind of get a sense for the maybe the hairstyle and the black and white picture there from that. But I'm not going to go into this too much, but the documentary is tremendous. It's also a case study in science not being used in the best sense at first, and it actually took a group of citizens to learn, essentially self-educate themselves, or self-educate in environmental toxicology, and to advocate and lobby and push legislators and even state scientists in New York to take this seriously. It's a hard documentary to watch. The things that the people went through in Love Canal were horrible. The cancer rates, the pollution of the soil, the effect on their health, their pets' health for generations. So I encourage you to watch it. And the woman in this picture was the lead of a group of mothers, actually, that led the charge. But more on the documentary. Again, I would watch it. I might make it part of an assignment, or if you want to do an extra credit summary essay or something like that. Now here, the main pollutant was not something that is in part 3 of the book. These were primarily organic chemicals that were manufactured, and you can see one of the names of those chemicals up there, dioxin. You can look up the chemical formula for that, or the chemical structure, or the MSDS sheet, I guess SDS sheet, safety data sheet. It's highly toxic, and that was dumped directly into the water. And then, like the Denora smog that we talked about outside of Pittsburgh and all the metal refining plants, I believe zinc was the primary one. The tragedy is what led to regulation. And that's one of the histories of environmental science in this country. It tends to take a tragedy, maybe that's just globally as well. It tends to take a tragedy before we start to take regulation seriously. And this is one I led to, not the Clean Air Act, but the Clean Water Act. Okay, so take a look at that. Pretty interesting. And so the part 3, water chemistry, water pollution, you can see that. Chapter 10, let me go back to that. Chapter 10 um, is substantial. It is the most mathematical. This is like chapter 1 from the atmospheric chemistry. So we hit it hard, and we go with a bunch of mathematics. And so there's going to be quite a bit of review to do. I'm going to mention a little bit more about the math on the next slide. There's not too many slides here. So that one is certainly the most challenging, and you can take a look there. I'm just looking through the flip through, and well, anyway, you can list that there. Now, the thing is, we still have to be selective. And so there's some things I'll do a ton, and then we'll go from there. The next chapters in this section are largely technological or engineering. Doesn't mean they're not important. They just tend not to be as theoretical, mathematical in nature. So chapter 10 is really the heavy one. And then chapter 11, pollution and purification of water. That's kind of important. So we talk about things like, well, how do we purify water with something like reverse osmosis? Or what are the main considerations with that? That is an enormously important topic. A desalination plant, for example, very expensive, very energy intensive to run something like that. So we'll talk about those different ways. And also, what do countries do in cases where they can't necessarily afford the most technologically advanced approaches to purifying water? Everybody needs water. And there's, again, no shortage of specific examples, including currently where I'm sitting in the Cumberland Valley. Some of the issues we're having with water are runoff from warehouses, and then, like a lot of the world, data centers being built up, and how that might affect things like erosion, introduction of other chemicals, things like this. So these are very, very important issues. And understanding the chemistry behind all of that will go a long way. So we're not just treating this as a collection of facts to memorize. We have a more of a mathematical perspective. And then there's a whole chapter devoted to toxic heavy metals. And in fact, when you leaf through to that chapter, you'll see that it's essentially dedicated, different parts of the book are dedicated to a specific toxic heavy metal. And you already probably know some of these, like lead and cadmium, and what are some of the issues associated with those once they get into the water. Okay, so that's really an overview of part 3, just in terms of the chapters, and a little bit of show and tell here. This was kind of when I taught the class face to face. I thought about pulling all these slides out, but I decided to leave it in there. Um, is when you do your independent project on climate change, it's really necessary to understand fossil fuels. And I apologize, you might know all of this already. So fossil fuels, I euphemistically, somewhat sarcastically, I suppose, refer to as the fuels that result from dead plants and animals in the ground. That's what they are. They are fuels made from fossils of plants and animals. And so I have a slide here for each of the major fossil fuels. You have natural gas, great. You have coal, great. And then you have crude oil slash petroleum, however you want to call it. So those are the three primary ones. Why am I doing this? The main thing is it is much of the global economy, and I'm not an economist, so I'm not going to make this an economics lecture, is based on fossil fuels, not just for fuel. So it's not just natural gas to heat your home or to light a Bunsen burner in a chemistry laboratory. So I think I've used some of these slides before. So on the left here, you have natural gas, and we've looked at all the different components of natural gas. Methane is the highest one. It depends on, it's not a uniform composition, but 80% methane. Then you have ethane, propane, butane, and you can read all of that. And I'm not going to do that there for you. And we also realized from the last chapter, in some cases, dihydrogen sulfide, the rotten egg smell, that if you've ever been near a leaking natural gas wellhead, like I have in Western Pennsylvania, hiking in the woods, can sometimes be the majority of natural gas. So this is not a constant composition. This is a typical composition. And then the infographic on the right, it's probably being covered up by my little circle with my head in it. Just shows you all the different things that natural gas are used for. In fact, a lot of plastics originate from natural gas. So you harvest the natural gas, you separate it into its various components. I'm not going into all that at the processing plant, but it's a good infographic. It didn't take me that long to find. And then sometimes you liquefy the natural gas, and we do this a lot in the United States. We export a lot of liquefied natural gas from seaports like Philadelphia, for example. We ship it over to Europe. So it's a big commodity, a highly profitable commodity that we export to other countries, somewhat because of the fracking industry. Also, you see in that infographic, maybe imperfectly, is the ethane, the C2H6 component of natural gas is vital. You take C2H6 and then you can manipulate it and go from all single bonds and you make a double bond in between the two carbon atoms. So that makes it not ethane, but ethene with a double bond, if you know your organic chemistry nomenclature, also called ethylene. Ethylene is a very, very important molecule. Without that, a lot of our economy would have difficulty going forward. Ethylene is used to make a lot of plastics, and you can see that there. Again, that's just the infographic. So what's my point? My point is natural gas is more important to the economy than just as a source of fuel. It does a lot of things. Similarly, and I actually did not know this very well prior to teaching this course. Coal, these are some of the molecules. Coal's complicated, right? You have anthracite, you have bituminous, you have lignin, you have all different kinds of coal. Anthracite's the hardest coal. So in Pennsylvania, northeast Pennsylvania had a lot of anthracite coal, like the highest quality. Still does. Where I grew up, there was some anthracite, but there was some bituminous. So it depends on where you are and how long the coal has been in the ground as to the degree of hardness and its usefulness as a fuel or in other things. So I put this here just because coal is very complicated. So if you want to know some actual molecules that are in coal, well, there's a graphic that I found. I'm not going to go through any of that. One thing I did not know was how coal, like natural gas, is used for a lot of consumer products. I suppose I should have known this. Maybe you knew this before. So this infographic just shows something similar to the natural gas graph that is used to make a lot of things. One thing that's kind of near and dear to my heart is I'm a cyclist, and I have two bicycles actually made out of carbon. Where does that come from? It's basically sheets of carbon that are then used to shape and make a pretty high strength material. Well, that comes from coal. I don't know if you can see that here. So that's called, I think they call it graphene. Yeah, graphene. And then you layer these sheets and make up a very, very light but very, very strong material that's used for all kinds of things. And one thing it's used for is in the military, it's used to make drones, believe it or not. So some drones that fly out there, um, either self-guided drones or drones that are controlled remotely, are made from graphene, which ultimately comes from coal. Okay, so that just shows you that coal is more than just something you burn in a power plant. There's a lot of consumer products that are reliant on that. And I think, where did I get this infographic? Yeah, there's some universities in coal country, like West Virginia, Kentucky, and there's probably some other ones in there that I can't read on the slide, that have these programs designed for this. Again, there are consequences for using coal. And then finally, I think maybe I used this infographic before. So petroleum is, you take the petroleum and you put it into basically a giant still, and then low boiling point things come out here, high boiling point, or sorry, low boiling point things come out at the top because they're already gases. Higher boiling point things come out the bottom because either they're just solid materials that are used for all kinds of things, like for paving roads and stuff like that. So it's not much of a sell to tell you that a lot of the world economy depends on crude oil. You probably already knew that. And the final graphic there uh, is is basically what it's saying is you have what is this graph? So it's energy density on one side. I think that's the y-axis, and then actual density on the x-axis. So the point here is this: fossil fuels are energy dense. They have an enormous amount of energy, potential energy put into them. They are extraordinarily hard to replace as a source of fuel and as a feedstock for consumer products. They are enormously difficult to replace. So to switch over to another kind of fuel is one thing, but to replace fossil fuels in our economy is a bigger challenge. I'm not saying we shouldn't try, but just to put this all in perspective, it's there's a lot to it, and this just compares, like, batteries, for instance, are pretty low energy density compared to fossil fuels. I'm not sure if nuclear is on here, but when it comes to energy production, it's hard to top either fossil fuels or nuclear. Okay, so that was just a little bit of show and tell, and we're already getting a little late into this video. And so when all is said and done with part 2, and actually really only chapter 10, because that's the one that handles most of the chemistry. So I want to give you a sense here, and the review problems will be vital. We have to look at, well, this might be about half of the general chemistry coursework that you had, maybe even 2/3 of it. So we have to remember redox chemistry. We had to do that before. So oxidation, reduction, that's fine. Another take-home message is, wow, is oxygen important? So that 20% of the atmosphere, that oxygen exists as a gas, when it dissolves in water, a lot of what we're going to talk about is the chemistry there. Is it happening in an oxidative environment? Is it happening in a reducing environment? So we have to combine those two things. So DO, dissolved oxygen. So it's not O2G, it's O2AQ. And what's the math behind that? Well, that's Henry's law. That's the partial pressure of the gas and the concentration of the gas at a certain temperature. So that's something we have talked about before. We got to remember all of our acid-base chemistry. I can't stress enough. Is, for example, is oxygen being dissolved in an acidic environment? Well, that affects the redox chemistry as well. Is it being dissolved in a basic environment? That affects the redox chemistry as well. So the type of water, the pH of the water, impacts everything. And then, so the acid dissociation. Okay, so I'm not going to read all that, but we also have to, now we're going to start introducing, water comes into contact with solid materials, soil, sediments, minerals, rocks. So we have this, well, how do we handle that equilibrium? Well, that's an equilibrium between a solid, and if the solid is ionic, like minerals are, and it disperses in, or it dissociates into its ions, that's characterized mathematically as a solubility product equilibrium, or KSP. So we have to know something about that. And then finally, I wasn't sure how to do this. There's different ways here. Is we have multiple equilibria happening at the same time. We cannot treat them in isolation. That's not the way environmental science works. It's difficult to look at one piece, which is one of the reasons I love it. So we have to think about complementary, which are sometimes called simultaneous, which are also sometimes called competing equilibria. I'm not sure why. I guess competing isn't a bad word because sometimes this equilibrium is more important than this equilibrium under these conditions. Okay, whatever. So multiple equilibria that we have to take into account at the same time, or under certain conditions, this one's more important and we don't have to worry about the other one. Takes precedent, if you will. So it's competing equilibrium between the atmosphere, the water, and soil sediment. So that's one thing. The nice thing is, I went ahead to this quote, so ignore that quote for a second. The nice thing is, remember, chemistry for us is a tool. I am not teaching you chemistry. I'm teaching you how to use chemistry to understand the environment. And when you have, say, 6 equilibria happening all at the same time, that sounds hopelessly complicated. Well, it's actually not. Well, how do you take 6 equilibria and chemical equations and combine them? Well, you add the chemical equations together. So if you have chemical equation 1, 2, 3, 4, 5, you add them together. And sometimes if you have to flip it or do something to manipulate it, okay, fine. But you add them together. That's thermodynamically legit, called Hess's law. Well, then what do you do with all the equilibrium constants associated with each one? You multiply them. So you add the chemical equations, you multiply the equilibrium constants, then you do something with that math. Okay. The authors of the book have some really excellent quotes. And it seems weird to talk about take-home messages before we've even done anything, but I thought I'm going to come back to these quotes, of course, and we're going to do all this math. Excuse me. I thought these were just kind of really good ones, and I just wanted to share them with you. I also learned to use the word instead of excerpt from a book. Somebody said extract is, I think, what publishers use. So these are extracts from your book. Sounds very chemical, doesn't it? So first off, natural waters in which this overall process, well, this overall process refers to all these equilibria happening at the same time, can be viewed as a big titration, that's cool, of an acid that originates with carbon dioxide from the air. So, okay, I didn't put CO2 there, but same idea. CO2G goes to CO2AQ, and that acidifies an aqueous system. So CO2 going into the water from the air acidifies the water. Bases can happen from various places, but if you have carbonate in abundance in the soil or rocks, minerals, what have you, limestone, for example, central Pennsylvania, then you have these competing ideas of acidification coming from the air, base from the soils and sediments in areas that have a lot of, I think they're called calciferous rocks, so limestone, I think that's the word, but anyway, carbonate. And you have to consider those. But I thought it was just kind of neat to think about it's an acid from the air, base from the soil and water as a titration. That's really kind of a neat way to summarize it. And the second one, I'm not sure I'm going to be able to read this because my face is blocking it during this recording. Thus, the acid reaction of dissolved CO2 and the base reaction of dissolved carbon have a synergistic effect. I just said that. Synergistic effect on each other, and that one increases the solubility of the other. So we have to consider these both in the same environment, and then what takes precedent, what ions are present under what conditions, and usually those conditions are 2, what redox conditions, and what pH conditions we have. Okay.